Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. So in today's class, we are going to discuss about the topic which is network theorems. So we have already discussed network theorems in the previous classes also. So these network theorems are especially with AC excitation. And in the previous classes, we have discussed superposition theorem, reciprocity theorem, and as well as Thevenin's theorem. So in today's class, we are going to discuss about the maximum power transfer theorem. So first, of course, this theorem already we have discussed when we are discussing about the DC networks. But once again, let me just recall the theorem, which is the maximum power transfer theorem. So here it is the statement for the maximum power transfer theorem. So here it states that in a linear bilateral network, maximum power is delivered to the load when the load resistance is equal to the internal resistance of the source. So, which is, I mean, this is actually mostly 70% is similar to that Thevenin's theorem. So here, this theorem states that the condition to get the maximum power, or the condition to find the maximum power flowing through the load resistance. Okay, at what condition the maximum power flowing through the load resistance? So, I mean, load resistance means, I mean, at a particular resistance where we need to find the total power delivered to the particular resistance, right? So here, let us consider this is the circuit. Okay, so in this circuit here, RS, I mean, VS is there, RS is there. So VS is the voltage source, and RS is, let us consider the internal resistance of the voltage source VS. Then here it is RL. So when RL is equal to RS at that particular condition, the maximum power will flow through the internal resistance, I mean through the load resistance. That is in case of I mean when it is a voltage source. But if you consider a current source, here, of course, the current source IS is also having the internal resistance. Let us consider RS. And in this case also, when RL is equal to RS, at that particular condition, the maximum power is delivered to the load of RL. This is the maximum power transfer theorem. Then, yeah, that's what here they mention. Okay, so when, I mean, if it is an independent voltage source, then its series resistance, or the, I mean, of course, the internal resistance is connected in series, its series resistance, or if it is a independent current source, then its parallel resistance or the internal resistance of the voltage or current must be equal to the load resistance RL to deliver the maximum power to the load. So this is the condition to get the maximum power to the load. Then what is that maximum power? Then how we can calculate? So as we know, P is equal to I square RL. Okay, so here I is equal to the total voltage Vs by the series resistance Rs, or the internal resistance of the voltage source Rs plus RL, that is the load resistance. Then substitute here P is equal to I square R. Okay, you know already I is equal to Vs by Rs plus RL. Then substitute in this equation, then you will get finally the power P is equal to Vs square into RL by Rs plus RL whole square, right? So in this way we can find. Then the condition to get the maximum power, here it is, because here RL is the variable, which means at what value of RL you will get the maximum power. So to get that, you have to differentiate the power with respect to the RL and equate to 0. Then you will get the condition to get the maximum power, which is RL is equal to Rs. Okay, so now the condition is Rs is equal to RL, or RL is equal to Rs, right? So to further understand this one, okay, let us take one example here. Okay, so this is now just now we have calculated, I mean, R, in another words, P is equal to Vs square by 4R, because here Rs is equal to RL, which is equal to R, let us consider. Then P is equal to Vs square by 4R. Then here, suppose let us consider Vs is equal to 10 volts and Rs is equal to 5 ohms. So for taking the different values of the RL value, okay, so let us find the power delivered to that particular load. So first let us consider here RL is equal to 1 ohm. Okay, Then let us consider, of course, if RL is equal to 1 ohm, then I is equal to, because I is equal to Vs by Rs plus RL. So then I is equal to 1.67 amperes, so that the power P is equal to I square R. If you substitute in that equation, then power that you will get is 2.778 watts. So which means when you consider RL is equal to 1 ohm, then the power delivered to the load resistance of 1 ohm is 2.778 watts. Then similarly, let us consider RL is equal to 3 ohms. Then again, substitute in this equation, then you will get the I value, which is 1.25 amperes. Then substitute this I value here in this, or in this equation, then you will get P is equal to 4.68 watts. Then find another value for the RL. So RL is equal to now 5 ohms, okay, which is RS. RS is equal to also 5 ohms. So which means at this particular case, we have taken the value of RL as a 5, same as the RS. So again, substitute in this equation, then you will get I value, and substitute in this equation, then you will get the P value, that is 5 watts. Then let us consider one more or two more values, okay, which is greater than the 5 ohms. Then let us consider RL is equal to 7 ohms. So when RL is equal to 7 ohms, then I will become 0.833 and P will become 4.86. Then similarly, RL is equal to 9 ohms. Okay. So when RL is equal to 9 ohms, then it is 4.59. As you can see here, the various values of the power for the various values of the load resistance that we are considered. Okay. So which one is the maximum value here? This 5 watts is the maximum value. Okay, so where we got the 5 watts, because where RL is equal to 5 ohms, okay, which is RS is equal to also 5 ohms that we have considered. So when RL is equal to RS, we are getting the maximum power delivered to the load, right? So this is how, okay, so we can find the maximum power delivered to the load at what condition, right? So if you draw a waveform for these particularly, then you will get, okay, for various values of the here on y-axis it is power and x-axis it is RL. By increasing the RL at a particular point, you will get the maximum power. Okay, so after that again the power will get decreased. Okay, before that also it was below that maximum value. Okay, so here at this particular case where RL is equal to RS, okay, then you will get the maximum power, P maximum. Then coming to the procedure. Okay, so how to find the RL means it is nothing but the R Thevenins here. So where RL is equal to R Thevenins, okay, at that particular case the maximum power will flow through the through the load, or the maximum power delivered to the load. Then let us consider a simple circuit, okay, with AC input. So find the load impedance in below figure for maximum power to the load and find the maximum power. So here there are two questions. One is, first we have to find what is the load impedance. Here this is the load impedance. We don't know the value of the load impedance. So first we have to find the value of the load impedance. Okay, and at what condition we need to find the load impedance? Okay, for the maximum power delivered to the load. Okay, so which means at what condition the maximum power will deliver to the load? When RL is equal to R Thevenins or RS. Okay, so in this case it is R Thevenins. Okay, so that's why first we need to find the R Thevenins value, then equate whatever the value R Thevenins that we are getting, okay, equate to ZL. Then at that particular case the maximum power will flowing through that or delivered to the load, so which means the ZL equal to Z Thevenins. Then by using again the equation, then we can find here this is the equation. P is equal to V square by 4R. By using this equation we can find what is that maximum power delivered to that load, right? Okay, so first here we need to find Z Thevenins. Okay, so for Z Thevenins we know already the procedure. First of all, we should know where we need to find the Z Thevenins, that is across the load terminals, which mean across these two terminals 1 and 2. And the considerations or conditions to find Z Thevenins is, okay, we have to replace all the voltage sources with a short circuit and the current sources with open circuit. But anyway, here we are having only one voltage source, and that voltage source we can replace with a short circuit. Then let me draw the circuit. Yeah, here. Okay, so and before that, here I have replaced this R plus JXC as a what is that Z1. Okay, and this is Z2, right? Okay, so that's why here instead of R and X, here I have just what is that taken as a Z1 and the remaining is a Z2. Now in between these two terminals, we need to find the Z Thevenin's value. Okay, so here it is very simple, as you can see. Okay, so as you can see here, it is very simple because here, as you know, here Z1, which is equal to the value of the R is, I mean, R minus JXC. Okay, so here R is the 6 ohms and XC value is 8 ohms, so J 8 ohms. So if you convert this rectangular form into polar form, then you will get 10 ohms at an angle of minus 53.3, sorry, 13 degrees. Then similarly here Z2 is equal to plus JXL. Okay, so which is equal to, let me see, yeah, JXL. So which is equal to J8 ohms. So this is J8 ohms, right? Now we need to find the equivalent impedance in between these two terminals. As you can see here, Z1 and Z2 are in parallel. So the Z Thevenin's, which is equal to Z1 Z2 by Z1 plus Z2. So here Z1 Z1 is here 10 ohms at an angle of minus 53.13 into, if you convert this one J8 ohms, okay, into polar form. So here you will get 8 ohms at an angle of 90 degrees. By here Z1 is 6 ohms minus J8 ohms plus Z2 is J8 ohms. Okay, so here plus J8 ohms and minus J8 ohms will get cancelled. Then you will get finally here it is 13.33 ohms at an angle of 36.87 degrees. So if you convert this into again rectangular form, then you will get here 10.66 ohms plus J8 ohms. So now this is the value of your Z Thevenin's. Now we need to find the E Thevenin's value also, because the equivalent circuit is having E Thevenin's and Z Thevenin's. Okay, so that E Thevenin's by 4, I mean the formula, the equation is here, it is Vs means nothing but the V Thevenin's or E Thevenin's. E Thevenin's square by 4R. So that is what here now we need to find. So then how to find the E Thevenin? So here E Thevenin's is nothing but the voltage across the impedance Z2. Okay, so simple, we can apply the voltage division rule now, because we know E and we know Z1 and Z2 value, so that we can find the voltage across the Z2. So here E Thevenin's, which is equal to, the total voltage is E into Z2 by Z1 plus Z2, right? Then substitute the values here. Z2 here it is 8 ohms at an angle of 90 degrees into here it is 9 volts at an angle of 0, which is E value, by here again Z1. Okay, let us write into the rectangular form, J8 ohms plus 6 ohms minus J8 ohms. So again here J8 and J8 gets cancelled. Then you will get finally the value of the what is that? This is 72 volts at an angle of 90 degrees by 6 volts at an angle of 0 degrees. And if you simplify further this, then you will get 12 volts at an angle of 90 degrees. Then now find the P maximum. Okay, so here it is, this is Z Thevenin's. Okay, so the first what is that question is find the load impedance. So here the load impedance, which is equal to RL, is equal to Z Thevenin's. Okay, which is equal to our load impedance. Let us consider here ZL instead of RL. So ZL is equal to Z Thevenin's is equal to 10.66 ohms plus J8 ohms. So this is the first answer. Answer for the first question. And for the second question is find the maximum power also. So here the equation for the P maximum, here it is E Thevenin's square by 4 into, of course here R. 4 into R, or 4 into what is that? Yeah, of course 4 into R. So here you will get here 144 by here 4 into 10.66 ohms. So then you will get here 144 point here 44.66. So you will get 3.38 watts. So now the P maximum, which is equal to 3.38 watts. This is the maximum power. So this is the way to find the unknown load impedance or load resistance value, and by after finding the unknown load impedance or load resistance value, then we can find the maximum power which is flowing or which is delivered to that particular load resistor or impedance. Then let us go for another problem. Okay, so it is little complicated than the previous one, because it was previously it was very simple. So of course this is also not that much very complicated, okay, but little. Okay, let us take this circuit. Okay, for this circuit again we need to find the same two things. One is the unknown load impedance, okay, when the maximum power is delivered to that load, and another one is the amount of the power which is delivered to that particular load impedance or the load resistance. Okay, so here also the same thing. First we need to find Z thevenins and as well as the what is that E thevenins. So after finding the Z thevenins, then the Z thevenins is itself the load impedance. Okay, so then after finding the load impedance, then we can find the E thevenins. So that after finding E thevenins and Z thevenins, then by using the equation P maximum is equal to E thevenins square by 4R, then we can find the maximum power. So first let us find the Z thevenins here. So here, to find the Z thevenins, of course, again the same way, we need to first get open circuit that particular what is that impedance. Okay, then in between those two terminals, we need to find the Z thevenins, and also we should replace all the voltage sources as a short circuit and the current sources as a open circuit. But anyway, in this in the given problem, it is having only the voltage source. So that's why here the voltage source is replaced with the short circuit here, right? Okay, so now here see, we can't say, I mean, which one is series and parallel, because as you can see here, of course, let us consider if these two, because we should not eliminate these two terminals, these two. Okay, so between 1 and 2 terminals we can't eliminate. So if you go with Z1 and Z2, because of course Z1 and Z2 is connected, but this is connected to the second terminal, so we should not eliminate the second terminal, and the third terminal is there. Here at the third terminal, there are 3 resistors are connected to this particular node. So that's why we can't say whether here the Z1 and Z2 are in series or parallel or something like that. Of course, here instead of Z1, Z2, Z3, I have just mentioned Z1, 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 all are Z1, because here as you can see, the values of XL all are same, all are 9 ohms only. So that's why instead of considering Z1, Z2, Z3, I have just considered Z1 only. Okay, so the remaining here, because this value is different and with these XL values, so that's why here I have just considered it as a Z2, right? So now we need to convert this first the star network, okay, this delta network into the star. So if you convert the delta network into the star, then here the network will be like this. So because anyway all impedances are same, so here it is Z1. Okay, then another here, let us consider, here it is again one more Z1, and here it is one more Z1, because this delta is we are converting into the star. Okay, so fine, of course this is the second terminal 2, and of course here again in between here it is one terminal 1 is there. So let us consider here again. Okay, then here, and after this Z1 Z2 is also there, because we have eliminated this one. Then here the third terminal, here it is 3. Okay, because anyway it is in between the 1 to 3 terminal only, so 1 to 3 terminal we have replaced the delta as a star, and again here one more what is that resistor is there, this is Z2, I mean the impedance is there, this is Z2. Okay, so again here we need to add these two, right? So this is how we can convert. So now let us find Z1 value. So here Z1, I mean by converting star to delta, so here the Z1 is equal to, okay, R to convert this one. Okay, so here Z1 is equal to, or yeah, Z1 is equal to Z1 dash into, okay, and no, first here we need to find, let us consider here not Z1, this one, this is because already Z1 dash, Z1 dash and Z1 dash, okay. So because here this is star to delta, because all are three, what is that, impedance values are same, so we can simply write here Z1 dash, which is equal to Z1 by 3. So what is the value of Z1 here? The Z1 is Z 9 ohms. Okay. So Z 9 ohms by 3. So which is Z into 3 ohms. This is the value of Z1. I mean Z1 dash, sorry. And similarly here Z2 is, the value of Z2 is 8 ohms. The value of the Z2 is 8 ohms. Right. So now if you redraw this circuit, as you can see here, this Z1 is connected to the open circuit. This Z1 is connected to the open circuit. So let us, I mean, it is in between 1 and 2 terminals, right? Okay, 1 and in between 2 terminals we need to find. So for one terminal here, the Z1 is there, or Z1 dash is there. Okay. So then after that here, then here for this terminal, I mean the second terminal, for the second terminal here, Z1 dash is there. Okay. So I mean for the short circuit it is connected to the Z1 dash, and these Z1 and what is that, sorry, these Z1 dash and Z2 are connected in series. Okay. So then here the Z1 dash and Z2, then okay, I mean here from Z2, here again the terminal 2 is there. Okay, terminal 2 here, this is 1, and let us consider here it is 2. Okay, because from here this total terminal is same. Okay, so that's why 2, and in between these 1 and 2, okay, so one more one more resistor is there, that is this Z1 dash. Okay, so that's why here from Z1 and Z1 dash, here it is from here, okay, from here to here. Okay, so this is the terminal. So in between again one more Z1 dash is there. So I have just redrawn this circuit is something like this. Now we can simply observe that Z1 dash and Z2 are in series, and this total combination is in parallel with the Z1 dash. So that here, then here Z1 dash is connected to open circuit. So here the current flowing through Z1 dash is 0, which is nothing but we can neglect this one. Then the total, what is that, the Z Thevenins across the terminal 1 and 2, which is Z Thevenins, which is equal to Z1 dash plus Z1 dash Z2 by Z1 dash plus Z2. Okay, then substitute the values here. Here Z1 dash is equal to Z3 ohms, which is equal to here Z1 dash into, sorry, here, yeah, Z1 dash plus, oh sorry, here it is, of course here it is connected to the open circuit, but here now we should consider this Z1 dash also, because here there is no voltage and current sources. Okay, so that's why here we should consider this Z1 dash also. So then up to this only we got, right? I have just made mistake here, this is not right. So here Z Thevenins is equal to, these two are in series, so here and this series combination is parallel with the Z1. Okay, and this total combination is in series with the Z1 dash. So that's why first let us consider here it is Z1 dash. Okay, here it is Z1 dash plus, and these two are in parallel. Okay, sorry, series. So and this series combination is parallel with this one. So that's why here Z1 dash by Z1 dash plus Z2 by Z1 dash plus Z1 dash plus Z2. Okay, so for better understanding, I can just place this one. Then substitute these values here. So here, then the Z1 dash, here it is 3 ohms. Yes, Z3 ohms plus plus z1 dash again. Okay, so z1 dash again, let us consider here because multiplication. So that's why I have just mentioning, or I have writing, I mean I have converted into polar form. So 90 degrees into z1 dash plus z2. So here again z1 dash is what is that, j3 ohms. Okay, plus z2 is, here it is 8 ohms by, then here of course here again we can write it as like z1 dash is again j3 ohms. Okay, plus j3 ohms plus 8 ohms. Then if you simplify this, then you will get finally, of course here j3 ohms. Okay, plus the numerator. Okay, let me write the same way, at the rate at an angle of 90 degrees, and j3 ohms plus 8 ohms. Okay, by here we can write it as j6 ohms plus 8 ohms. So now I am converting everything into the polar form. Okay, so except this j3 ohms. Okay, and here if you convert into the polar form and multiply this what is that things, then you will get here 25.62 at an angle of 110.56 degrees by, again here j6 ohms plus 8 ohms also I am converting into the polar form. So here it will become 10 at an angle of 36.87 degrees. Then if you simplify this, then you will get here j3 ohms plus, and again after just simplifying this, then it will become 2.56 at an angle of 73.69 degrees. Then again if you can further simplify this, then the Thevenin's, which is equal to 0.72 ohms minus j 5.6 5.46 ohms. This is a Z Thevenin's. So now this is the answer for the first question, that is what is the value of the load resistance, or the load impedance, that is ZL. So here ZL, which is equal to Z Thevenin's, which is equal to this value. Then now we need to find the E Thevenin's value. So for the E Thevenin's value here, of course here as you can see in the circuit, in the given circuit, this one is there. Okay, but we need to find here. Okay, we need to find here, but of course for that again we have simplified the circuit, because after we are converting delta into star and all, so we are simplified. Then for the E Thevenin's, the circuit will become the similar way. Okay, so this is just let us consider here it is Z1 dash, and again one more, here it is Z1 dash, and it is Z2. So and in between these two combination, Z1 dash is there again, but there is an voltage source. Okay, so here this this voltage source in series with this R, what is that, Z1 dash. Okay, so here it is plus minus, and this is E. Okay, of course AC anyway. Yeah, so this is the simplified circuit for this E Thevenin's. So now we need to find the E Thevenin's across these two terminals for this particular circuit. Then how we can find these E Thevenin's? Again here also the same way. Okay, here for E Thevenin's, okay, which means here the voltage across these two terminals we need to find. Okay, so the voltage. So for this here, the E Thevenin's, which is equal to Z1 dash plus Z2 into E by Z1 dash plus Z2 plus Z1 dash, because now we know the total voltage, and then simply apply the voltage division rule, then you will get. So by substituting the values of Z1 dash, Z2 and Z1 dash, of course here the Z1 dash is equal to say 3 ohms, and here Z2 is equal to 8 ohms, and E is equal to 10 volts at an angle of 0 degrees. So substitute all these three values in this particular equation, then you will get finally the E Thevenin's value, which is 8.54 volts at an angle of minus 16.31 degrees. Right. Then now P maximum. Now we need to find P maximum is equal to E Thevenin's square by 4 into R. then E Thevenin's is 8.54 whole square by here 4 into R is 0.72. Then finally you will get here it is 25.32 watts. This is the P maximum value. Right. So this is how we can find the maximum power which is delivered to the load, and we can find what is the load resistance, the unknown load resistance at the condition when the maximum power is delivered to the particular load. So this is how we can apply the maximum power transfer theorem to the electrical circuits with AC. Okay, or the AC electrical circuits. In the next class, we will discuss the next topic, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.